This conference will now be recorded.
Very good evening, students. Today we'll be continuing discussions with electrostatic potential or electric potential energy and electric potential and relation between electric potential and field. This particular topic. So we will be first taking one numerical problem on electrostatic potential energy. Then I'll just enter into electric potential, and there also we'll be taking various examples. Okay, so let us start with this numerical problem on electric potential energy. So in this question it is said 2 point charges Q1 and Q2, they are equal to 2 microcoulomb, are fixed at x1, which is 3 meter, and x2, which is minus 3 meter. You can see this here. So Q1 and Q2 both are of 2 microcoulomb, and their position vectors are with respect to origin. This O is origin here. So this is plus 3 meter and this is minus 3 meter. Okay. A third particle of mass 1 gram. A third charge particle which has mass 1 gram and charge minus 4 microcoulomb. Are released from rest at y is equal to 4 meter. So the third charge is actually released from this particular place, which has vertical coordinate 4 meter at this position. Okay, so what we need to find out is the speed of particle as it reaches the origin. Speed of the particle as it reaches to the origin. Okay, this is the question. We have to find out the speed. So you can see that the electric force here if you see this, electric forces are acting this way and this way, and there will be net force like this. Okay, these are symmetrically, so these points actually are symmetrically situated from these three. Okay, Q3. I mean, if you look, the system will be like this. So there will be forces like this, and this resultant will be acting towards the origin. So you need to find out the speed when the particle reaches here. So anyway, this distance, you know, this initial position, you know, initial velocity is 0, it starts from rest, that is also fine. So to find out the final velocity at this particular position, you need to know the acceleration, but in this case it is not the constant acceleration. As you see that the electrostatic force will be actually variable force, because as the distance changes the force changes, and hence there will be no kinetic like constant acceleration. But you can calculate that just at some certain point you can calculate that acceleration, but you may not be able to get this acceleration, constant acceleration, very easily. So what is the easiest method to solve this problem is to use the conservation, law of conservation of energy. Okay, use law of conservation of energy. So that will be the simplest way to solve this problem. Use law of conservation. We have to actually find out the final velocity of this particle, which was like charge particle, which is left from here 4 meter above the origin. Okay, so when it reaches near the origin, what will be the speed of that particle? That is what is the question here. So we have to use law of conservation of energy. So how do we use that? So at this particular position, see the total energy is how much? How much is the total energy? What is the kinetic energy at this position? Ki initial kinetic energy is 0 because the charge is at rest. What is the potential energy? So potential energy, this we can find out. Potential energy we can find out due to this two, sum of these two. Okay, potential energy. So when this charge particle is here, so potential energy between this. As you know, for multiple charge particles, we know how to calculate electrostatic potential energy. I'll write it just few minutes later. Okay, so this is non-zero value. This is non-zero value. Now when it reaches here, we have to find, we can write here the final kinetic energy, suppose V. So sorry, final velocity V. So half mv square will be the kinetic energy. And what will be the potential energy? Potential energy will be again depending on the positions. Okay, so potential energy also obviously will be there. So both kinetic energy and potential energy will be there at this particular position. Okay, whereas at this position, since the object is at rest or the charge particle is at rest, so it will not have any kinetic energy. Okay, so with this, if we try to solve this, see, first of all, 1 by 4 pi epsilon naught r. This I am taking common. So initial potential energy I am going to write. So what is that initial potential energy? So suppose this one, Q2, Q3, Q1, Q3 like that. And also here is this Q1 and Q2. So Q1, Q2 by Q1, Q2 by R12 plus C Q1, Q3 will be there divided by R13. Then Q2, Q3 okay, this is the potential energy initially. Okay, we can calculate if we want, but anyway we will write first what is the, so here if the velocity of the particle is this v, so you know we get half mv square. But what about uf 1 by 4 pi epsilon naught. So q1 q2, that is 2 1 or 1 to 2 1, let us say. So this is 3 1, say. So in this case, you need to remember these are actually initial distance. These are initial distance. Here somehow these are actually final when it reaches to the origin, nearly to the origin. So then potential energy. So if we go ahead with this calculation part, see what Q1 and Q2, Q1, Q2 are 2 microcoulomb and Q3 is 4 microcoulomb. Just one thing. So look, we have got the charges here. Now it will be easier for us to calculate things. So we have ui plus ki is equal to uf plus kf. So this is the formula. So this is 0 anyway initially. So we had 1 by 4 pi epsilon naught, then 3 2 or 2 3 whatever it is. This is initial position. And Q2, Q1, so this is equal to, on the other hand, final. This is also final. Okay, so this is the law of conservation of energy I have written for both sides. See, one thing you can note that, see, the distance R12 or 21, they are actually same. 2 1 is also this distance, 1 2 also is this distance. So this distance are same. So 1 2 and 2 1, they will cancel each other from both sides. So these two terms will cancel each other. Now rest of the thing we have to put the values and find the numerical values here. So look now, for this, we can write 9 into 10 to the power minus 9. So Q2 and Q3, that means 2 microcoulomb into, here I can just multiply 10 to the power minus 6 as well. 2 and 3, R23, 2 3, this one will be actually 5. So 3 1 also will give you 5. 3 means 4 into 1 means 3. So similarly on the other side, see what you can write. So this term will be common from both sides. So 2 3 is again 2 3. Distance is now 3. because it has come here at the origin. We are just supposing. And 1 3, okay, 2 there was minus, actually 2 minus will be there. And Q3 actually is minus 4 microcoulomb. We have done some mistake here, calculation. Q1, Q2 are 2 microcoulomb and Q3 is minus 4. Let me write it here. Two microcoulomb. So according to this, if we do the calculation, 2 3, so 2 3 2 3 is minus, right? 3 is minus 4. So this one, and this is actually see 3 1 3 is minus 4 and 1 is 2. Like that, here also minus 4 into 3, sorry, minus 3 2 minus 4 into 2, then 3 1. Only thing is the distance in this case now it is 3, okay, 3 meter. Because that distance will be this one actually now after the charge being here. So minus 4 into 2 divided by 3 2, that will be this. And on the other hand this is 4 1, sorry, 3 1 3 1 means again then this is R31, again this is 3. So along with that there will be half m v square. M is 1 gram, so we'll put that 10 to the minus 3 and all. Look, if we simplify that, what we get? If we simplify that, what we are going to get is see 9 into 10 to the power minus 3. Sorry, this is actually 10 to the power 9, not minus 9, 10 to the power 9. So 10 to the power minus 3 whole into minus 16 by 5. Okay, on the other hand, there will be 9 into 10 to the power minus 3 here, it will be minus 16 by 3 plus half m, that is 10 to the minus 3 v square is v square. So if we just do the simplification, so if we do this calculation carefully, we will be able to find out v is equal to 6.2 meter per second. Okay, so this is the answer for this question. Like, what is the velocity the ball will sorry, this third charge will attain when it reaches to zero origin? Now we will move on to the topic called potential. So what is electric potential? Just like electric strength, coulomb force per unit charge was electric field strength. Similarly, here potential energy is potential is the potential energy per unit charge. So it is denoted by V. So potential energy U by Q0. Okay. See, electric potential energy at any point, electric potential at any point in an electric field is defined as the potential energy per unit charge at that particular position. Okay, just like definition of field strength. So that is electric potential. Now this electric potential can be expressed in terms of work done as well. It could be explained in terms of work done as well. So how do you do that? See, we know change in the electric potential energy is equal to minus work done, A to B. So change in so I'm sorry, this is so this is what we get from here, change in the potential energy and work done. Now so here we can see U by Q naught, that means work done per unit charge, and this could be even written as VA minus VB okay. So this is VA minus VB is equal to WAB uh, divided by Q0. Q0 is the charge taken. So this is the way to find out, or this is the definition, kind of definition we get for this electric potential. And electric potential can be simply written in this way also. See, this one is the work done per unit charge. Okay, so now we'll calculate potential, electric potential. See, there is an example I have taken here. electric potential at A point is given 20 volt, and B point it is given as minus 40 volt. So here what we have to calculate? We have to calculate work done by an external force, then and electrostatic force in moving the electric charge slowly from B to A. Okay. So suppose there is a position A, this is B. Okay, so this is the one. So we have to take a charge from one point to another. What is the work done? So look, VA minus VB is actually work done divided by Q. Okay, that is what we have seen just previous slide. So work done, there are two work done, so you have to calculate here. One is work done by external force, and another one is work done by the electrostatic force in moving an electron from B to A. So how to do that? Here there are two potentials, so we have to take the an external put, then moving an electron. Electron is this way, so we have to actually so electron is carried from B to A. So work done will be actually the charge and potential difference. This is minus 40, 20. Electron charge is, see, then it is actually minus 20 into 10 to the power minus 60, the minus 19 charge. Okay, so what we are trying to get is, we are trying to get the work done due to external force. Work done due to external force, that is always actually negative. Okay, so let me just modify a little bit this one. So work done by external force. So work done by external force. So that is W is equal to Q into Q0 into VA minus VB. VB. Okay, so eventually it will be 9.6 into 10 to the power minus 18 with the minus sign here. This is the work done by external force. So what about work done by this Udar Govinda? So we'll see what is the work done. This is actually joule. Work done by electrostatic force. What is that? That is, see, we have to find out like this. So WB2A, that is equal to minus WB2A that is minus into the external work. So WBA, this by electric force, this by external force. So this is actually external force. All right. So what we get here, minus of minus 9.6 into the minus 18. So it will be actually positive. So this will be 10 to the power minus 18. Okay, so minus 18. All right. So we can see here that the work done by external force is negative. Okay, and work done by the electric force is actually positive. Therefore, we may say that whenever charge particle go from lower potential to higher potential, then the work done is negative. When it moves, see, when a positive charge move negative charge moves from a lower potential to higher potential, the work done by the electric force will be positive. When the positive charge moves from lower potential to higher potential, then it will be negative work done. So this is the thing we have seen here. Okay, so we'll just move on to the next topic. So electric potential due to a point charge. So electric potential due to a point charge. See, if I have a point charge in any point, so we know potential means electric field divided by unit charge. So for this, the Q0, the electric field is we know that the electric field is Q naught at any point. If we want to find out the so Q0 by 4 pi epsilon naught R square, this is electric field. Then electric field similarly, okay, so electric field strength we got like this, EQ by this, right? E by Q0 we got this. So similarly here also, if we find out the potential energy, So the potential energy will be this. If we just remove this, what is the potential for it? Then you have to just multiply. Sorry, this is Q epsilon naught R. Okay, so this will be actually, so due to a point charge, you have to calculate this. Okay, so this is point charge. We'll go to calculate the electrostatic potential energy due to some static charges. System of static charges, when we use a system of static charges, then how to write down the potential? C summation over Q by Q by, say 1 by 4 pi epsilon 0, that is common. Q by R, Qi by Ri. Oh, sorry, this is, anyway, we'll just go for this. So this is actually the potential energy for uh, a set of charges. That means you can just like electric field superposition principle, here also will be followed by the charge particle. So here 1 by 4 to epsilon naught, and this is Qi by Ri. Okay. Okay, so if this charge is not a point charge, if it is a distributed charge, then we can get distributed charge will be this. So this is for continuous charge distribution. Continuous charge, okay. This is for isolated charge. Okay, so isolated charge. So now we'll go for one or two application part. So we'll take up one example. So this is example of one. Here, due to this, we have to find out the potential. So what is this? I'll just write down the question, just a minute. So the question is that four charges are placed. Four charges are placed on the vertices of a square as shown in the figure. All right, so here you have to find out the electric potential at the center of the square. So V electric potential at the center of the square will be 0 as all the charges are at same distance from the center. Okay, so we have to find out the potential at here. So how do we find out the potential? We have to actually find out so Q net in this system, actually net charge is actually 0. Q net is 0 in this case. Net Q is 0. Example, okay, so net charge is actually 0 here. Okay, so we'll just actually you might be thinking why what is the value of this electric potential at the center? It will be 0 because the potential due to this two will be, see, I have to take the summation of all, right? So if I just calculate due to this, then positive 8 microcoulomb. So potential will be due to this charge at this particular position. See, anyway distance are same, so I'm just taking minus 4 microcoulomb by some distance, say this is suppose AO. Similarly, from this position it will be actually minus, so this is V1, this V2 will be again. This is also suppose BO. A, B are same actually height. Okay, so you can sum these two off, and this also, and this also you can the sum of. So you'll get say total V net to be 0 here at the center. Okay. Okay, so I think if I start this, it will take little longer time. We'll stop it here for today. We'll take up next day very nice examples and numerical problems. Thank you for your patience. Bye for today.